1.1 is general models. All right, so different forms of machine learning. They don't use this a lot today, but a lot of companies use this in certain capacity. Don't get stuck on one type of model, and this is why I tried to loop initially. Try to use the best one that fits the scenario you're working on for a more broad case of AI. So support vector machines, random forest, logistic regression, k-means clustering, k-nearest neighbors, Bayesian models, and neural networks. And I kind of put it in order of what I feel is most used down to at the bottom. So all the hype now, of course, is in neural networks. And then Bayesian models is something I personally like using because they have a very accurate statistical approach to getting towards a solution like neural networks. All right, so support vector machine. It's pretty much a high-dimensional system of vectors. Shown over here where you can kind of break or classify 2, 3, or more systems apart from each other using a hyperplane in the middle. I'm not going to go into detail about this because I just don't have the time for each one. But you can see here, there's a classification system that separates 2, 3, 4, 1,000 classes from each other. And you're able to predict, based on the next value put into the system, if it fits in this region, you can identically, classify it as class 2 or as class 1. And I only show you 2 classes here, but like imagine there's many more. This hyperplane here separates the differences between the two. And it allows you to kind of separate the different classes. Moving on.
Is class just like a generic classification?
Classification.
Okay.
Yes. Oh, did I go backwards? Okay. All right, so random forest is focused mainly on going through or traversing through a system and trying to figure out what the best solution is. Also another statistical process as well to figure out that everything we're talking about today is based on classes. Most of the time it's class-based, classification-based. There's other levels, but this is classification-based we'll talk about. And when I mean classification, what I mean by that is recognizing what something is. So I can recognize a person like Marina, I recognize her, or I recognize a chair. I can recognize the differences between the two. So if I look at an image, for example, I can recognize the different parts in the image, and that's classification. I can classify it through this network. So random forest, for example, I can recognize different items from that. And this, again, is numerical. Now, logistic regression can be used both in a binary system or it could be multinomial, which is not linear regression, which you probably learned in school. Linear regression is typically just a slope, and you separate the two apart. Logistic regression it can be multiple variables put into this, and it's separated through some line, as shown here, of what is true or false. And that, again, once you build that model and you add or introduce a new value to it, and it kind of helps you determine which side it's on and classify it again. All right, so same thing I mentioned before, logistic regression. Now this is the multinomial version of this, of regression. This is now, again, classification, but at a high dimensional vector space. So more than 5, 10, 100,000, depending on your compute speed. Now, Bayesian models, now this is getting into a little more high-level mathematics, statistics, and this gets into a distribution. So you can compute in here, let's see if I had it in here, the next layer. Yeah, the probability of one state giving another. So the probability that I'll come to work given that, my kids were help me today to get to school, whatever scenario you talk about. What's the probability of a scenario happening given a lot of different scenarios? And you see over here, broken down in 3 parts, but it's broken down into infinite level of classifications. So again, we'll go into it. There is a posterior, which is calculated. There is the likelihood calculation, the class posterior probability, and the predictor. Typically, it's 3 parts, but you see 4 here, but typically 3 parts, broken down into the prior, the likelihood, and the posterior. And typically, the posterior is the end result. The likelihood is something that could happen given different states, And the prior is something we do all the time. The prior is a state where we think about something we already kind of have a judgment on, but we need the exact likelihood to help make the difference. Any questions on that? Was that clear? No? Okay, perfect. All right, so again, Bayesian models and multinomial. Now, one of the great things about this is you are able to break it down, and this is Star Trek, Next Generation. Right? Some Trekkie geeks in here, I know. If you were to run a Bayesian model based on words that are said in a movie against these different people at the bottom here, and you ran into a Bayesian model, you can see the heat map here showing what's the probability of certain words said versus for a particular person. So if I were to say, if I were to put a collection of these different words together into a model and then make the prediction, I can highly predict that, for example, Troy or Riker could say something based upon certain words together in a group. And that allows me to figure out if my solution is correct or not. All right, so good and bad of the Bayesian model is not as fast or not as wonderful as a neural network, because neural network is more accurate. But what I like about the Bayesian model is there is a little bit of variance of error, similar to how we think, because it introduces some curiosity into the model. And that's why Bayesian is one of the ones I like. All right, so neural networks. This is something we'll get into heavy. We have 86 billion neurons in the brain. That's a lot. And we have about 1,000 trillion synapses. That's almost infinite amount of data. So what I mean by that also is measure a bee. A bee has about 1 million neurons, and the level of complexity of the bee is pretty simple. Eat food, do whatever it needs to do. A dog has about 530 million neurons as well, which is an order of about 160 times less than we do. And that allows us to think at the level we are. So imagine if there's a system who had more than 86 billion neurons. What kind of level of complexity would it have? That's what they're trying to work on in AGI. So moving forward. So we're going to get into some deep stuff here. So neuron core is broken up into parts. There's the dendrites, there's the axon, there's the cell body, and there's the synaptic part at the end of the axon, where it allows you to be able to connect from one neuron to the next. And you'll learn this in neural networks, but this is just something that works in our brains currently. A little more detail about that. So I made the connection between how it's done in artificial neural networks versus how it's done in our actual physical brains. Again, dendrites, cell body, axon, and a terminal axon is what we call here an activation function. So when once the cell body says enough axon potential goes through this system and turns on and sends the signal across, it actually charges and creates an activation function in the neuron, and you see it over there, the f of x, and sends that signal forward into the next neuron. And you can see down here, between them is something called synapse, or synapses, or between the two, the dendrites, or the axon here, axon terminal, and the dendrites on this side. And in the middle here, you can see that this typical neuron or a neural network you see if you work in this field, you'll see those connections there. And these lines here are the actual synaptic connections. Those are where in our brain we have about somewhere between 100 to 1,000 trillion connections between the neurons. It's a lot. Okay, so here's a little model of how making a prediction from one item to the next, to the next, to the next using a neural network. This is DeepMind's version when they were working on like initial AlphaGo. I'm not gonna go into that because everyone talks about that. But you can see here, it spreads out, makes one decision, that's the best decision, and go from there. So it's something we call data explosion. It's just a significant amount of data that can be computed. That's why you need large machines to compute this level of networks. And this is a feed-forward artificial neural network. And we'll talk about what feed-forward and backprop means in a little bit. Any questions? Is it a lot so far?
It's a lot.
There's a lot more. So we have in here in this neural network a system where each one of those green items up there are inputs. And each one of those green items are like, for example, a feature. They call them feature sets. And a feature set can be, for example, I identify a person. One feature set can be a hair, the hair color, the shirt they're wearing, the facial expressions. And you'll see this in artificial deep neural networks. Each one can be some level of input that's signaled through to give me to identify a person, for example. So I send a person through, the network will figure it out, and then at the end, it will give me an answer or a solution to whatever it is I'm trying to figure out. And typically, we use something called supervised learning for this, because we send a value in, and we get an output out. Simply put, same thing, goes through, computes the values, output. And this is a loss function. You guys are familiar with this concept, which is basically just going through, backpropping through the entire system and literally going back to the very front again, making a correction to it. So to make that kind of connection, you learn something, right, and someone smacks you in the hand and says that's wrong. Well, it goes through the whole system, figures out, okay, what did I do wrong, and do it again. This loss function kind of denotes that in mathematical terms. All right, so for a backprop, you see here it's going forward, they're going to set it back. Basically correct what it saw to fix it, and then that's where all the math comes in using partial derivatives. And does that over and over again so it feeds one input, set of input in, goes through the system, figures out, makes a correction on that, and then send that back, and that's one cycle. That's one cycle. All right, so artificial neural networks are much better than all the other models out there because artificial neural networks are able to have such high accuracy of predicting a value, and that's why a lot of people use them. The hype is huge on that. So this is a visualization of a clustering all the different types of classifications. You can see by the colors. It clusters things together based upon what are likely to be similar to each other. So similar to how the brain region works, where certain areas are like specialized for images, which is the back area of the brain, or language, which is area of the region of the brain. Your deep neural network should be able to do the same thing, and it's visualized in this way. All right. So I'm not going to get into math yet. That's going to be the next section. But just to kind of get over this, mathematics of artificial neural networks is using matrix multiplication. Pretty much it's all it uses for the most part. So if you guys ever took linear algebra, you hated it? Well, that's going to be a problem. Because, well, actually it's not. Because a lot of people now use models like Cure or whatever, or TensorFlow that already does this. So you don't have to actually learn this stuff. You can go straight to the actual models or the actual libraries, and all you need to do is put in your data, use the libraries, and you should be able to go through this without having to know all this math. So I'm teaching you the math now, but you don't actually have to know it all. You just need to have an understanding of it. But matrix multiplication is linear algebra, and it's a simple concept where you just multiply the top row by a column, and then it ends up being a new matrix, n by m, and that's what I would do at the end of that. All right, so we are typically going to start with simple recognition. Most AI is about recognition, recognizing something. You have a certain input, recognize the output. So I recognize, simply put, I recognize that you are here. Or I recognize you're not here. Or it's binary, however you want to put it. Whatever domain you're working in, it has a lot of significance. And most of our brains now work as recognition systems. All right, so before we end this part, where there are some different types of compute you'll look at, there are typical CPUs. We tried that, that didn't work very well. So we went into GPUs, which is graphical processing units, which is what most machine learning is using today to compute this high level of matrix operations. Because GPUs are pretty good for doing matrix operations, because it's just multiplying numbers together, GPUs are used for this. And you ever seen those racks of this GPUs just sitting out there, people using computing? This is what they're doing with it. And then there's TPU, which is this Google version of a GPU, which is this the same thing, just Google putting their name on it and optimizing it, where it's basically about 5 times faster than them and a lot cheaper in cost. You can't actually buy this. You have to use their services. That's kind of how it works. Okay, so in neural networks, we have scalars, vectors, and tensors. This is where you get the whole term TensorFlow, because it's a matrix inside of a matrix, which is the last part over there. Vectors are just, again, I showed you before, one column by one row. And of course, scalars are just one particular value in the matrix. All right, that's literally the end of the first section. Any questions?
How do you determine the structure of the neural network? Like initially you showed a diagram of a neural network which has 16 or some numbers,
Yep.
and then there are 7 layers. How do you determine the number of neural networks in each layer?
Typically, you define the level by choosing your own size. There's some things where they actually choose the number of nodes you're talking about. Yeah, the number of nodes or neurons in there. You can choose your own size of neurons. So for example, if I took a picture in there, a 28 by 28 photo, right, and I want to send it through, all you're going to do is extract the features from that photo. So I say I might want to have 1,000 in there to help discretely figure out each node to have a specific abstraction of the photo. So the more the better, but you also have to think about the level of compute that you have to deal with.
Does the result change if I choose a different number of neurons in each layer?
And the accuracy does change, but if you're talking about the number, well, it depends. If you use more nodes in one layer, it helps a lot, but if you have more layers to go through, it'll be more accurate. But the problem is, again, compute. I would probably say I probably stay low within 1,000 or less, because it gets cumbersome to have that many in one vector. But then you have multiple layers in that neural network.
Will you talk further? Will you go over the activation function and how it actually?
Yeah, we'll go over that.
Like implement a curve, like.
The sigmoid curve?
Yeah.
Yeah.
How does it fit into a curve? Like if you want to predict something which goes into a curve, right? How does an activation function, which is simply, if it's taken, it's very simple. But how does it work to generate a curve, for example?
Oh, the actual function 1 over e, I think it's 1 over 1 plus e to the, we'll talk about that in a little bit. Yeah, but we don't actually use that anymore, we use ReLU.
Yeah, ReLU.
Yeah, actually the one we use.
ReLU seems to be a binary, right? 0 or 1.
No, actually can go beyond 1. It actually just takes from 0 to any number beyond that. It doesn't have to go to 1. Any other questions?
Oh, just a simple question. I mean, what's the difference between what Microsoft is offering and they're offering Amazon and Google? You get the TensorFlow. I'm not sure what the Amazon is. Is it just compute that's?
Actually, I'm going to go into a whole section on that in the next section. But I can talk about that. So Amazon has their I gotta look at the list again. I typically don't use that one. But then TensorFlow is a whole complete platform. So they do not only provide you the models, but also provide you the APIs and the production level readiness versus like Akira's, which is just good for practicing on certain models and figuring out how it's used. And you can test it out with Keras, but you can't use production level for that. It's more for a beginner level. Or PyTorch, which is good for research, but it's also not good for production level as well.